It's gonna be a nice and easy day right here. Nice and easy day. Let's look at what we're getting into. It's gonna be real quick. All right, here we go. So as we discussed in the previous section, exponential functions are used for many real-world applications such as finance, forensics, computer science, and most of the life sciences. Working with an equation that describes a real-world situation gives us a method for making predictions. Most of the time, however, the equation itself is not enough. We learn a lot about things by seeing their pictorial representation, right? And that is exactly why graphing the exponential equations is a powerful tool, right? So that's what we're doing today. We're going to be graphing them, right? It gives us another layer of insight to predict future events. All right. This is going to be real simple. I'm going to show y'all the hack right now. This is the hack right here. So graph and exponential functions. So before we graphing, right? It is helpful to review the behavior of exponential growth. Recall, right, the table of values for a function of the form f of x is equal to b raised to the x power, whose base is greater than 1. We'll use the function f of x equals 2 to the x, for example, right? Observe how the output values in table 1 changes as the input increases by 1. So our function is f of x is equal to 2 to the x, right? All I'm doing is I'm plugging in some x values here, right? Plugging in -3, -2, -1, 0, 1, 2, 3, and I'm just seeing what happens, right? And here's my output, right? For -3, I have 1 over 8. -2, I have 1 over 4. -1, 1/2, so on and so forth. Just plug in the value for x. That's it, right? So each output value is the product of the previous output and the base 2, right? So we call the base 2 the constant ratio, right? In fact, for any exponential function of the form f of x is equal to a times b to the x power, where b is the constant ratio of the function, this means that as the input increases by 1, the output value will be the product of the base and the previous output, regardless of the value of a. So here's what I want y'all to notice from the table right here, right? This is really important. The output values are positive for all values of x, right? No matter, so as x is going to negative infinity and positive infinity, all the values are positive, right? All the y values. As x increases, going to positive infinity, the output values increase without bound, right? Which means just goes to infinity, it just shoots up, right? As x decreases, going to negative infinity now, right? The output values grow smaller, approaching 0, but it will never actually get to 0. All right. So that's something real important to notice. I want to just give you guys a graph so you guys can see what's happening here. So this is it. So this is the graph. F of x is equal to 2 to the x power, right? Now, I want you to pay attention here. Whenever you're graphing something, right, I need to see some points on your graph, right? For the exponential function in particular, I need to see the y-intercept, right? So this crosses the y-intercept at 0, 1. And then if you can, give me some more points on the graph, right? The more the merrier, right? I'm not gonna like penalize you if you don't give me any of the smaller numbers. Like for example, you see how we have like -3, 1 over 8, -2, 1/4 and stuff. That might be really challenging to graph on the graph. So I don't really expect you to graph that, you know? But like the 0.12, the 0.24, that's fair game, right? 3.8 is kind of pushing it, but if you can, thank you. You're saying, all right? Also, you want to note when you're doing the graph, right? I want to clearly see that the horizontal asymptote is y equals 0, right? I want to clearly see that, right? So the x-axis is an asymptote, right? And then notice that the graph gets close to the x-axis, but will never touch it. Right? So that's that. See? Huh? Yeah, we're starting that. So the domain of f of x is equal to 2 to the x power, right? Is all real numbers, and the range is 0 to infinity, right? So for the exponential function, right? Your domain is all real numbers, negative infinity to positive infinity. Your range is from 0 to infinity, right? And the horizontal asymptote is going to be y equals 0, the x-axis. Right. Horizontal asymptote, right? So to get a sense of the behavior of exponential decay, we can create a table of values for a function of the form f of x is equal to b raised to the x power, right? Whose base is between 0 and 1. We'll use the function g of x is equal to 1/2 to the x power. Observe how the output value in table 2 changes or will change as the input value increases by 1, right? So all I'm doing, I'm just plugging in my x values, -3, -2, -1, 0, 1, 2, 3, right? And I'm just getting my answers out. So 1/2 raised to the -3 power is 8. 1/2 raised to the -2 power is 4. 1/2 raised to the -1 power is 2. 1/2 to the 0 power is 1. 1/2 to the 1 power is 1/2, etc. You just plug in the value for x and boom, you get the y value, right? Well, let's talk about it for a second, right? Again, because the input is increasing by 1, each output value is the product of the previous output and the base or the constant ratio 1/2, right? So the output values are positive for all values of x, all right? So no matter how x is going to negative infinity, x is going to positive infinity, the y values that you're going to get out are going to all be positive for the exponential function, right? As x increases, goes to infinity, the output value grows small, right? So notice that we have a fraction base here, right? So as x is increasing, right, the graph is getting closer and closer and closer to 0. It's not going to touch it, but it's going to get closer, really, really close to 0, right? As x decreases, goes to negative infinity, the output value grows without bounds, so it goes to positive infinity, right? This is what happens when your base is a fraction. When your base is a whole number, it's the reverse. All right. So real quick, just want to show you guys a graph so you can see what I mean. You can kind of tell from the table, but sometimes the picture kind of helps a little bit. All right. So this is g of x is equal to 1/2 raised to the x power, right? So notice how this is like kind of the reverse of what we were talking about before. This is like a reflection over the y-axis, right? So then that would flip it over the x-axis. Yeah. But notice how this graph is real quick, right? It's the reverse, right? As x is going to positive infinity, it gets close to 0. As x is going to negative infinity, it goes to positive infinity, the f of x, right? When you're graphing this, I really, really, really need to see the y-intercept as 0, 1. If you can, give me some more points on the graph as well, right? Like -1, 2, that's reasonable. -2, 4, reasonable. -3, 8, I'll accept the argument that you feel like, all right, that's pushing it. I get that, right? And the other side that's getting really, really close to 0, I'm okay with if you don't show me that on the graph. I mean, like it's really hard to do, like 2 and 1/4, huh? Yeah, that's essentially that's what I'm saying. I want you to label it, label the graph. you know? But give me some points on it. Don't just draw the picture. Give me some points on it, you know? That's what I want. And of course, the x-axis is the horizontal asymptote as well. All right. Just want to say on a side note, so the domain of g of x is equal to 1/2 raised to the x is all real numbers, and the range is from 0 to infinity, right? And the horizontal asymptote is y equals 0. No vertical asymptote here. Yeah, not for the exponential function. Yeah, it is a function though. It passed the vertical line test. Yeah.
So we just have vertical asymptote in the rational function. Okay.
In the polynomials and the rational functions, right. Yeah, no, the rational, no, what you said, the rational functions are the ones with the vertical asymptote, right?
The exam I was so
Yeah.
I mixed everything.
Oh no, it's not that bad, I promise. All right, pay attention to this next part right here. This is really important. This right here is the sauce. This is everything you need to know for the homework. And one little easy to read gray image, right? So characteristics of the graph of the parent function, f of x is equal to b to the x power. An exponential function with the form f of x is equal to b to the x power, where b is greater than 0, so b is a whole number, and b does not equal 1, of course, right? It has these three characteristics. Hmm?
It's not that.
No. We're done with that. Yeah. Yeah. But that was a good formula though. That was a good one. That one you just showed me. Yeah. That was a good formula. Right? So these are some of the characteristics of the graph where b is bigger than 1, right? It's bigger than 0, screen positive, right? It's a whole number, right? So it is a one-to-one function, right? So every x has its own unique y value, right? It has a horizontal asymptote at y equals 0, the x-axis, right? The domain is negative infinity to positive infinity, right? It's important to know. The range is from 0 to infinity, right? The range is from 0 to infinity. The x-intercepts, it has no x-intercepts. This does not touch the x-axis. All right, it will not touch the x-axis. Right. It gets close to 0, but it'll never touch 0. Right? Their y-intercept is going to always be 0, 1. Unless, of course, there's some kind of shift or something. But for the most part, it's 0, 1. Right? It will be increasing if b, the base, is bigger than 1. It will be decreasing if b, the base, is less than 1. So if I have 3 raised to the x power, that's an increasing function, right? Or what you call it, exponential growth, right? If I have b as a fraction, let's say 1/3 raised to the x power, right? All right, that's a decreasing function or like exponential decay, right? That's the difference between them. All right. So this one picture right here, this is the sauce right here. That's the sauce. Real quick, I just want to show y'all side by side what these two graphs look like. Go ahead. Yeah. And yeah, new homework is posted. In case y'all want to take a look. It was easy, right? No? All you gotta do is just type in this thing. This will answer the whole homework.
It's only this month.
Just this one. Just this time.
Only like
Unless there's a shift. Yeah. But you'll see it. When you do the table of values, it'll pop to you. All right? Remember, y-intercept is where x equals 0, right? Y could be anything else, is where x equals 0. So real quick, I just want to show you this side by side so you can see. So the graph on the left, right, like right over here, this is our regular formula. This is f of x equals b to the x power, right? This is the way it looks. I definitely need to see that y-intercept, right? When x is 0, what is y? And give me a point on the graph, any point, just give me something. Give me something. The flip side now, right? This is when our base is less than 1, right? Meaning that our base is a fraction, 1/3, 5/8, whatever, right? And then raised to the x power, of course. This is how the graph will look. Again, when you're graphing it for me, right? I need to see that y-intercepts, and just give me another point on the graph, right? I don't care if it's like on the left, on the right. If you can give me multiple points, thank you. Like the more the merrier. All right. And that's it. Label your graphs. That's what I'm trying to say. In more words than few. Okay. Let me give y'all the T real quick. Yeah, I can't leave y'all hanging without telling y'all about this. So here's a little how-to. So given an exponential function of the form f of x is equal to b to the x power, we're going to graph the function. Here's how you do it. Step 1, create a table of points. All right. You don't have to be every single point. Just create a table of points. My favorite numbers to plug in for x, -3, -2, -1, 0, 1, 2, 3. Those are my favorite. All right. Plug them in. Yeah, those are your x's, get your y values, boom, right? Step 2, plot at least 3 of the points on the table, including the y-intercept. I need the y-intercept. I'll accept it with one more point, but if you can, just give me as many as you can, please. All right. Step 3, draw a smooth curve. The more points you give, the easier it is to draw the curve because you're just connecting the dots. All right. Step 4, the domain for the exponential function is -infinity to +infinity. The range is from 0 to infinity, and the horizontal asymptote will be at y equals 0, right? Unless there's some kind of shift upwards or something or down. But generally speaking, that's it. So let's take a look at this, right? This is an example. So sketching the graph of an exponential function of the form f of x is equal to b to the x, right? We're going to try and sketch the graph of f of x is equal to 0.25 raised to the x power. We want to state the domain, the range, and the asymptote. All right. So let's make a table of values, right? I have x and I have f of x, which is equal to 0.25. That's the same as what, like 1/4, something like that? Yeah. So like 1/4 raised to the x power, something like that, right? So anyway, plug in some of my favorite numbers, right? All right, I'll be honest. I really didn't like the 3. I was just saying the 3 because that's what was in the table, right? My favorite is -2, -1, 0, 1, and 2. Those are my favorite numbers. If needed be, I can do other ones, all right? Another way I like to choose my numbers too, you notice how this is like 1 to the 4th? No, excuse me. You notice how this is like 1/4? So maybe something in the 4 power, You know, just my preference. Do what you like, you know? So anyway, let's look at the first one, right? The first one's gonna be what? 1/4 raised to the -2 power, right? So we already know whenever you have an exponent and it's raised to a negative power, it's gonna go into the denominator, right? So this is gonna become 1/4 squared. Not quite, not quite, not quite. You push it into the denominator, then you're going to square the top and the bottom, right? So this is going to become 1/16, as you said, right? Keep, change, flip, right? So just plain old 16, good. And we do the same thing with the -1, right? So that should be what? +4. Anything to the 0 power is 1, right? 1 would be just 1/4. And 2 would be, I don't know, what's that? 1/16, something like that, right? So now with this knowledge, I can graph this, right? Nice and simple, nice and simple. So, right? Some points that I have, right? I have 0, 1. Boom, this is 0, 1. I have, let's see, 1 is 1/4, is 1/4, whatever that is. 2 is 1/16. All right. -1. There goes -1. It's +4. All right. So that's 1, 2, 3, 4. -1 is +4. Boom. So I could keep going, but from this, I can tell that my graph is going to look like this. Going to come down and it's going to go across like that. And that's it in a nutshell. That's all I'm looking for, right? What's my domain? Exactly. -infinity to +infinity. What's my range? 0 to infinity. All right. And what's my asymptote? What is that? I'll give y'all a hint. That's X, that's Y. What does this graph get really, really close to? 0 on the X or on the Y? On the X axis, which is what? Which is Y equals, right. Right. So we have an asymptote at Y equals 0, more specifically horizontal. And that's it. So all we had to do. Questions on this, anybody? You didn't even have to remember the two graphs because what do we do here? We make a table of values, we plug in the values, and boom, it tells us what's going to happen. That's all we need. Up and down is range for the Y. Yeah. Because it is going from 0 to positively all the way up. Yeah, without bound. You guys try. That's okay. You can describe it in words. It's fine. Y'all good? All right, let's try this out. So I got my input, output right here. Put in my favorite numbers, -2, -1, 0, 1, 2. Keep it simple. So I have 4 to the -2 power. This equals 1/4 squared, 1/16. All right. So this is going to be 1/4. Anything to the 0 power is 1. This is just 4. And then this is 16. All right. That's my table of values. Just plug them in. Nothing crazy, right? So we're going to make our graph. I need to see that y-intercept, right? There's that 0, 1. All right. Next, I see 1, 4. So this is 1. and 4. So that's 1, 2, 3, 4. Right here, that's 1, 4. And then 2, and then 16 is somewhere up here, whatever. All right. And then as it turns negative, all right. After that, just connect the dots, right? You get the idea. All right. Questions on this? What's the domain? Good. What's the range? Good. Asymptote?
Zero.
What 0? Which one? Very good. All right. So we good? All right. Even though I'm not going over this extensively, you all have enough knowledge to follow what I'm about to show y'all. All right. So this is a translation of exponential functions, right? So a translation of an exponential function has the form, right? A B raised to the x plus c power plus d, right? Where the parent function is y equals b to the x power, where b is greater than 1, right? So it will get shifted horizontally, right, by the c. So if c is negative, we're going to the right. C is positive, we're going to the left. Y'all remember that, right? It will get stretched vertically, right, by a factor of a. So the constant that's outside, right? Like either pull it up, pull it down, whatever, right? So it's a stretch if the absolute value of a is greater than 0. It's a compression if it's a fraction, less than 1, greater than 0. It will get shifted vertically, the graph, by d units. D is positive going up, D is negative going down. And we will be reflected about the x-axis if the a term in front is negative. All right. So these are the transformations for the exponential functions, right? Not going to dwell on this because you all know how to do this already. Just wanted to show y'all, right, that they exist.
They say it all.
Mm-hmm.
No, I'm kind of like that. So when they say that absolute value, that the a by itself, but not the a squared. Absolute value is just
Right. Right. How many units away from 0 it is. So any questions on this? All right. Y'all can knock out y'all homework with this. Let's move on. Oh, what happened? Give me 1 second. Okay. New topic. All right. Whew. It's an earthquake in Japan, this picture that you're looking at. So in 2010, a major earthquake struck Haiti, destroying or damaging over 285,000 homes. 1 year later, another strong earthquake devastated Honshu, Japan, destroying or damaging over 332,000 buildings, like those shown in the figure, right? Even though both caused substantial damage, the earthquake in 2011 was 100 times stronger than the earthquake in Haiti. How do we know? The magnitudes of earthquakes are measured on a scale known as a Richter scale, right? As a little side note, I don't know if y'all know this, but we actually have a Richter scale at BCC. It's in Meister Hall, on the main floor, if y'all ever want to see it. Pretty cool, all right? All right, anyway, I digress. The Haitian earthquake registered a 7.0 on the Richter scale, whereas a Japanese earthquake registered a 9.0. All right.
So I bet I've been close to down, right?
Cool. Yeah, it would tell us. Yeah. I mean, on campus though, we kind of safe. Like, yeah, yeah. I mean, the basement not so great, but like here and stuff. Yeah. Hmm. Yeah. That joint gets flooded when it rains though. I can't explain how. I can't explain how. But yeah, yeah.
To have a good thing,
Mhm.
the water right next to five and you would, I'm like, five.
It would rise, but it won't rise to where we are.
This thing just go like that.
Yeah, yeah. Like you remember when we was in class, I think it was last week or the week before, when like we had that rainstorm outside, right? Like, no lie, I remember looking out the window and I'm like, oh, it's raining. Like it didn't look that bad. But social media the next day, yo, yo, that joint was crazy. Oh man. Like, I'll say, but like for us, it was a normal rainstorm. Like, like it was annoying, but All right, so look, the Richter scale is a base 10 logarithmic scale. In other words, an earthquake of magnitude 8 is not twice as great as an earthquake of magnitude 4. So it is 10 raised to the 8 minus 4 power, which is equal to 10 to the fourth power, or 10,000 times as great. So in this lesson, we will investigate the nature of the Richter scale and base 10 functions upon which it depends. All right. So we about to get it in. It's gonna be fun. Oh man, this is my specialty right here. Excited to show y'all this one. All right. So we're gonna be converting from logarithmic to exponential form, right? So in order to analyze the magnitude of earthquakes or compare the magnitudes of two different earthquakes, we need to be able to convert between logarithmic and exponential form. For example, suppose the amount of energy released from one earthquake were 500 times greater than the amount of energy released from another. We want to calculate the difference in magnitude. So the equation that represents this problem is 10 to the x power, which is equal to 500, where x represents the difference in magnitude on the Richter scale. Well, let me ask you, how are we going to solve for x? Let's talk about it. Let's talk about it. This is going to be real dope. Hmm? Right. An inverse, kind of, right? So we have not yet learned the method of solving exponential equations. None of the algebraic tools discussed so far is sufficient to solve 10 to the x is equal to 500. We know that 10 to the second power is equal to 100, and we know that 10 to the third power is equal to 1000. 500 falls between 100 and 1000, right? So it is clear that x must have some value between 2 and 3, since y equals 10 to the x is increasing. We can examine a graph, right? As you can see right here. So we're trying to find out what is 500. What's that x value for 500, right? We know what 2 is 100, and we know what 3 is, that's 1000. But what is that value in between? That's what we're looking for. So what value can I raise? No. What number can I plug in for x? And that's going to be the power of 10 to get it out to be 500. That's what I'm looking for.
This is like crazy.
No. It's math simple, I promise. Nah. Nah, that's gonna be like, huh? Good. That's it, actually, yeah. That's it, yeah. Yeah. I got you. I got you. Well, we're gonna talk about it. Look, so estimating from a graph, however, is imprecise, right? To find an algebraic solution, we must introduce a new function. So observe from the graph, right, that passes the horizontal line test. The exponential function y equals b to the x is 1 to 1, right? So its inverse, x equals b to the y, is also a function, right? Also is the case with all inverse functions. We simply interchange x and y, right? And solve for y to find an inverse function. We know how to do that already, right? To represent y as a function of x, we use a logarithmic function of the form y equals log base b of x, right? The base b logarithm is a number, right? The base b logarithm of a number is the exponent by which we must raise b to get to that number. We read the logarithm expression as the logarithm of with base b of x is equal to y, or simply log base b of x is y. We also say b raised to the power of y is x because logs are exponents, right? For example, the base 2 logarithm of 32 is 5 because 5 is the exponent we must apply to 3 to get 32. Since 2 to the 5th power is equal to 32, we can write log base 2 32 is equal to 5. We read this as log base 2 of 32 is 5, right? So we can express the relationship, right? We can express the relationship between the logarithmic form and the corresponding exponential form as follows. Check this out. So log base b of x, right, is equal to y, and we can flip that around to say that b to the y power is equal to x, where b does not equal 0, and b cannot equal 1. Note that the base b is a positive number. It's always positive. So that formula right there, very important. Very, very important. We're going to use it in a little bit. Because logarithm is a function, it is most correctly written as log base b of x, using parentheses to denote the function evaluation. Just as we would with f of x, however, when the input is a single variable or a number, it is common to see the parentheses dropped and the expression written without parentheses. As log base b of x, notice that many calculators require precision, right? No, excuse me, require parentheses around the x. So we can illustrate the notation of logarithms as follows. So log base b of c, right? And then we're gonna switch the base and the answer, and then switch the answer and the x value to get b raised to the a power is equal to c. All right. So note that comparing the logarithmic functions and the exponential functions, the input and the output are switched, right? This means y equals log base b of x and y equals b to the x power are inverse functions, okay? Yeah.
Negative power
Mm-hmm.
also equals, whole thing over 1.
Mm-hmm.
So,
Let's talk about the definition of the logarithmic function. A logarithm of base b of a positive number x satisfies the following definition. For x greater than 0, b greater than 0, and b does not equal 1, y equals log a base b of x is equivalent to b raised to the y power equal to x. All right? Where We read log base b of x as the logarithm with base b of x or the log base b of x. The logarithm y is the exponent to which b must be raised to get x. All right. Also, since the logarithmic and exponential functions switch the x and y values, the domain and range of the exponential functions are interchanged with the logarithmic functions. Therefore, the domain of a log function is from 0 to infinity, but the range of the log function is from negative infinity to infinity. All right? Let's keep that in mind.
Yeah. The second logarithm
Mhm.
is that's negative factor to the
B is the base. The base that,
line.
yeah,
The domain is reduction.
right.
It is the inverse of exponential.
It is. Log is the inverse of exponential. Exactly.
Like,
Ex-
I was glad when I said, B greater than 0. So, or it had
You mean for the domain? It's the way the graph is, right? I can find some number that I can raise to the zero power and get one out. That's why being able to have that. Mhm. I got you. We're gonna look at an example in a little bit. So real quick, note, can we take the logarithm of a negative number, right? Take the log of a negative number. No, because the base of an exponential function is always positive. No power of that base can ever be negative. We can never take the logarithm of a negative number. Also, we cannot take the logarithm of 0. Calculators may output a log of a negative number when in complex mode, but the log of a negative number is not a real number. Right? It's imaginary.
big, oh,
Right.
yeah.
Mm-hmm. Right. I'll give y'all a little bit of tea. So given an equation of log base b of x is equal to y, convert it to exponential form. So here's what you want to do. Step one, examine the equation y equals log base b of x and identify the b, y, and x. Step two, rewrite the log base b of x equal to y is equal to y as b of x is equal to x. All right. You guys try. You good? Okay. So let's look at A. I have log of base 6 to the square root of 6, right? So I want to change this into exponential form, right? So base 6, right, raised to some power, let's call it x, is equal to the square root of 6, right? We could fix up that square root of 6 a little bit more. This becomes 6 to the x power is equal to 6 to the half power, right? Then x equals a half. Not bad, right? Good. Let's try the next one.
Well, this one, we have for this, right?
Mm-hmm. Yep, they gave it to us. We just manipulate it.
We got.
Mm-hmm. Basically, we're doing a conversion. That's why it looks like that. Right? Which 6? Because did a conversion. Yeah. So it really is this part that I'm talking about. Kind of like here.
Oh,
Mhm. Mhm. That's it. Yeah. So let's look at B. I have log base 3. All right. Um, so what I want to know here, right, is 3 raised to the second power. Does that equal 9? Right? And 9 equals 9. And that's it. Hmm? X is 9. Or, no. I guess there's no work to do on this. It's just convert it because there's no variable there. You know? But does this make sense to everybody? Good?
Yeah, I looked it up. Got it, so, 16, 16, 15.
The what?
I would like to start the model because like 16, 15, once again, it's a energy solved triangle.
Interesting.
Yeah, yeah,
Yeah.
think about how you did.
Mhm. Really interesting. Yeah.
Basically said to like try to
Mhm.
calculate the big triangles that should be all.
Yeah. Yeah.
I don't know why, yeah.
We'll see. Maybe we'll see. You guys try. Remember, you just converting it. Just convert it. You're good to go. What, the first one? 6. Mhm. I'll show you. Oh, it's not bad. So for A, right? I'm just converting it. This is log base 10 of 1 million is equal to 6. Convert it. So this is 10 raised to the 6th power. Does that equal 1 million? Right? And that's it. Yeah, they're both equal. And that's it. Let's try B. So for B, I have log base 5 of 25 equals 2. Right? So 5 raised to the 2nd. Right? Whoops. Yeah. And then 25 does equal that. Questions on this? I haven't really gotten to the math part yet, just rewriting. Mm-hmm. Okay. Like how to switch it over? Let me generalize it. It might make more sense, right? If you have log of, let's say, base A, B, that's going to be equal to the x power, right? So what this means is I'm look at the base now, right? For base A, I want to raise that to the x power and let that equal B. And that's how you go back and forth. Sometimes you need to do this because log is kind of hard to do, but it's easier to get an answer through the base. So converting from exponential to log form, right? To convert from exponents to logarithm, we follow the same steps in reverse. We identify the base, component x, and output y. Then we write our answer as x equals log base b to the of y. You guys try. I want these turned into logarithms. So I want log of base whatever equals whatever. Let's switch this up. Let's look at A. 2 to the third power equals 8. I'm going to switch this into logarithmic form, right? So what am I looking for? I'm looking for log of base 2 for 8 is equal to 3. Good, right? Questions on this? Or are we good? It's the same thing for the rest. Got you, got you. Got you. Huh? Exactly. Exactly. For this one, right? Log base 5 of 25 is equal to 2. That's it. Let's try C. 10 to the negative 4 power, we're saying is 1 over, right? 10,000. Second, so this is going to become log of what? 1 over 10,000 is equal to negative 4. That's it. Questions on this, anybody? I'm not gonna lie, this is your whole homework, so if you want, just type it in, boom, 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 and that's it.
You get formula earlier.
Yeah, same thing. And when you're on your test and you forget the formula, it's on your formula sheet. All right.
Then, it like, you doing the same thing, like, then,
Yeah. Do we need to do this or we get the idea I can move on? We can move on? All right. Yeah. Huh? You want to do C? All right. Let's see C then. So for C, so log of base what? 2 equals negative 1. Perfect. That's it. That's it. Yep, that's it. Yeah. It's the same thing though, no? Oh, there's no base there. Ah, my man. I'm glad you noticed that. All right. Nah, there's a reason for it. That's actually our next lesson. All right. So let's move on. So this is evaluating logarithms, right? So knowing the squares, cubes, and roots of numbers allows us to evaluate many logarithms mentally. For example, consider log base 2, 8. We ask, to what exponent must 2 be raised in to get 8? Because we already know that 2 to the third power is 8, it follows that log base 2 of 8 is equal to 3. Now consider we have log base 7 of 49 and log base 3 of 27 mentally, right? We're asked, to what exponent must I raise 7 to get 49? We already know that 7 to the second power is equal to 49, therefore log base 7 of 49 is equal to 2. We can also ask, to what exponent must 3 be raised in order to get to 27? We know that 3 to the third power is 27, therefore log base 3 of 27 is equal to 3. Even some seemingly more complicated logarithms can be evaluated without a calculator. For example, say we have log base 2/3, right, of 4/9, and we want to do that mentally. So we ask, to what exponent must 2/3 be raised in order to get 4/9? We know that 2 to the second power is equal to 4. We know that 3 to the second power is equal to 9. So 2/3 squared is equal to 4/9. Therefore, log base 2/3 of 4/9 is going to be equal to 2. Simple, simple, simple. All right. Yeah. Plus, yeah. Plus, y'all got calculators, so y'all could always like check it.
Like one of those things where like it could be just that simple, right? Like once you like write the formula over and over,
You just get it.
simple as y mx plus b.
Exactly.
Have y of them, have x of them, okay, so you
Exactly.
and you know,
Mhm.
plug and play with it.
Exactly. Exactly. It's all the same.
I have another question.
Go ahead. Huh?
You know the one that go out there, you didn't get a fraction.
So sometime, yeah.
Oh,
Yeah. So the negative is what pushes it to the denominator. That's the trick, you know? So that's why when you have like a fraction with it, that like that might be a negative, you know?
okay, fine.
Yeah. Especially when you see it like flipped and stuff like that, that's a negative that's being involved. Yeah. But don't worry, not that bad. All right, check this out. Given a logarithm of the form y equals log base b of x, we're going to evaluate that mentally. So here's how you do it mentally in your head. First, you rewrite the argument of as x as a power of b. So b raised to the y power is equal to x. Then you use your previous knowledge of the power of b to identify what y is asking. So to what exponent should b be raised in order to get x? All right. This is how you do it mentally. All right, check this out. I'm about to show y'all how to do this by hand real quick, right? So we want to solve y equals log base 4 of 64, right? That's a little bit complicated. So let's rewrite this. Let's rewrite it, right? Essentially, what am I asking you? I'm asking you 4 raised to the y power is equal to 64. I don't know why I keep doing that, right? So I want to know, right? Hypothetically speaking, 4 raised to what power would give me 64? Well, let's see. You're saying it's to the third. Let's see. So we know that 4 times 4 is 16. 16 times 4 is what? 32. Yeah, it is to the third. So y equals 3. And that's it. All right. Questions on it? Anybody?
I guess that's the thing. So that you and
Yeah.
So we need to make sure it's not providing maybe
Right. Well, the root will always be the same, but what would the exponent be? That's the trick. That's what I want to know. You know? Yeah. Yeah.
is it are we allowed to have the maintenance? So
Nah, no remainders. Yeah, these are gonna be nice. These are gonna be nice. Yeah. Like, look at this one real quick. So I want to solve y equals log 121 of 11, right? Without using the calculator, but we could use a calculator, right? So I have y is equal to log. I can't spell log. Let me try it again. Log of base 121 of 11, right? So what am I asking, right? I'm asking, right, for base 121 raised to the y power, right? what power can I raise it to get 11 out? That's what I'm essentially asking. What is it? Not 2. What is it?
Well,
No. No.
11.
Not 11. You're on the right track, but it's not 11 that I'm looking for.
No, it's not 11.
No. You're close.
Negative two.
You're close.
1/2.
Now we're talking. 121 to the half power, right? That's equal to 11. Let me say it a little bit differently. The square root of 121 is 11, right? That's what it is. Right? Fun, right? Not too bad. Yeah. Yeah. What's up? Yeah. Now I'm gonna get to the negatives that you were asking about. All right. So look at this now, right? So this is evaluating the logarithm of a reciprocal. All right. So watch this one now. So I got y is equal to log of base 3 for 1/27. Right? So what am I asking right here, right? I'm asking 3 raised to the y power is equal to 1/27. Right? So what do we think? How do I get 27? It's -3. That's the answer. So to push the 3 into the denominator, right, you got to make it negative, right? So I'm trying to think how I could show you this. So 3 to the y, this would be like 27 to the -1 power,
So
and then 3 to the 3. Uh-huh.
the exponent is there.
Yeah.
so why would it be, to the 1/3 power?
Because that would be the cube root of it.
Isn't that what we do? We're speaking,
But we're not cube rooting the 3. If the base was 27, okay, but the base here is 3. So that's why it's like that.
so what's the difference between a negative power and fractional power?
So negatives drop the whole thing into the denominator, right? The fractions are roots. Yeah. Not bad. You get it like with practice,
But, get the, with,
Yeah. My fault. I don't know what that was. Try this out. What do you think? Y equals log of base 2 for 1/32. So essentially, I'm asking you 2 raised to the y power is equal to 1/32. So what y'all think?
Negative one.
Negative what?
32 is
five.
no. 32 is the 4, 3,
I think it's -5. Yeah.
5.
Yeah. Because 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2, 32. Yeah. So 2 to the y is equal to 32 to the -1 power. And then 2 to the y is equal to 2 raised to the -5 power. So y equals -5. Not bad, right?
Like,
Uh,
and like, how many pounds to Like you get 32.
I like that. Yeah.
Okay.
Yeah.
That's fraction, right?
Yeah.
But at the same time, only a fraction
Yeah.
because it is negative.
Right. I agree.
You know, when they teach you how to solve for it,
Yeah.
put it over one.
Mhm.
That's
I agree.
something else.
I agree. I agree most definitely. All right. So now to your question from before. Using common logarithms. All right. Sometimes you may see a logarithm written without a base, right? When you see one written this way, you need to look at the expression before evaluating it. It may be that the base you use doesn't matter. If you find it in computer science, right? You'll it often means log base 2 of x. However, in mathematics, it almost always means the common logarithm of 10. So in other words, the expression log of x means log base 10 of x. All right. So that's the trick right there. You see me write log of x? It means log of base 10 of x. All right. Let's talk about that common logarithm again, real quick. So a common logarithm is a logarithm with base 10. We can also write log base 10 of x simply as log x, right? In your calculator, when you click log x, it's base 10, right? So you guys know. The common logarithm of a positive number x satisfies the following definition. So for x greater than 0, right, y equals log of x is equivalent to 10 to the y power is equal to x. We read log of x as the logarithm with base 10 of x, or log base 10 of x. The logarithm y is the exponent to which 10 must be raised to get the x value. All right. Not too bad. Not too bad.
And so like with that, you keep it straight line.
Oh, like to graph it? Yeah. We're gonna get to that. We didn't get to that today, but we're gonna get to that. Yeah. So currently, right, we use log base b of x, lg of x as the common logarithm, right? lb of x as binary logarithm, and ln of x as the natural logarithm, right? So we write lg of x without specifying the base is now considered bad form, despite being frequently found in other materials, right? So don't write lg of x, all right? Nah, don't do LG. Just to tell you about it. Because you might see it in some YouTube video or something. They saying LG of X, like just know it means base 10 of log, but it's not correct. It's not proper. Yeah. So given a common logarithm of the form y equals log of x, evaluate it mentally, right? So that's how you do it mentally. Step one, rewrite the argument x as a power of 10. So 10 to the y power is equal to x. Use your previous knowledge of the powers of 10 to identify y by asking to what exponent must 10 be raised in order to get the x power out. And that's it. All right. That's how you do it in the head. All right. Let's try it out. So you want to evaluate y equals log of 10 of 1,000, excuse me. Y equals log of 1,000. just like that, right? So we know this is going to be what? 10 raised to some y power is equal to 10,000, right? What's the answer? Third power, right? So y equals 3. Here's a trick, right? You just count the zeros. 1, 2, 3. All right. So that's 3. Yeah. Yeah, I got you. 10,000 though would be what? 4, right? Just for fun, real quick, just for fun, in case we win the lottery tonight. What's the answer? Right. 6. Huh? Say it again.
I said this one.
Yeah. What would it be? 6, exactly, right? So y equals log 1 million, right? It means 10 raised to the y power is equal to 1 million. You could just count the zeros, so y equals 6, right? Not too bad, not too bad. It's the inverse of the exponents. Yeah. How I use it when I get some kind of polynomial exponent question or whatever, I don't know what to do. I use this to put it in the calculator. You know, I just don't have time to show y'all that. But if y'all come to tutoring, I got you. I'll show you how to do it. All right. So, right? So using natural logarithms, right? The most frequently used base for logarithms is E, Euler's number, right? The value of which is approximately 2.71828, cool, right? Base E logarithms are important in calculus and some scientific applications. They are called the natural logarithms, all right? Love base E in calculus, right? Love that ln. Yes. So the base E logarithm, log base E of x, is known, it has its own notation, ln of x. Right? So when you see ln of x, that means log of base E of x. All right? Right here. This is ln of x right here. When you see that, it means this, log base E of x. All right? ln. Yeah. And it stands for natural logarithm. Most values of ln of x can be found only using a calculator. So sad. The major exception is that because the logarithm of 1 is always 0 in any base, ln of 1 is equal to 0. For other natural logarithms, we can use the ln key that is found on most scientific calculators. We can also find the natural logarithm of any power of e using the inverse property of logarithms. All right. So we building up to that. That's coming. Let me just talk about natural logarithms a little bit real quick. Just want to make sure y'all get this, right? So a natural logarithm is a logarithm with base e. We write log base e of x simply as ln x. The natural logarithm of a positive number x satisfies the following definition. So for x greater than 0, y equals ln x is equivalent to e to the y power equal to x. We read ln x as the logarithm with base e of x, or the natural logarithm of x. The logarithm y is the exponent to which e must be raised to get x. So since the functions y equals e to the x and y equals ln x are inverse functions, the ln of e to the x is equal to x. I shouldn't have told y'all that because that's going to appear on the test, but my mistake, all right? So for all x, right, and e to the ln x equal to x for x greater than 0, all right? Hmm.
He is usually above the pressure.
E is Euler's number. That's the 2.7, like this number here. 2.71828, that thing. That's E. Yeah. Yeah. Euler's number.
Just for this.
Yeah. Yeah. All right. Questions on this? It's there was a formula for one over no 1 + 1 over n something. Yeah. It's similar to the what you call it, compound interest formula. It's that. That's how you get E.
That's right.
Yeah.
That's like
Yeah. Yeah.
for make it flat and the kind of.
Right. Yeah. All right, so we good?
Yeah.
All right, bet. Do your homework.